what if the variable of a function, the variable on which a given function depends on, in itself is yet another function? What happens in that case, right? For example, something like this. Let me take, and you already know the derivations of, assuming that you know the derivation of log x. So d by dx of log x, as you already know, is 1 by x, and d by dx of x to the n is n into x to the n minus 1, and then d by dx of sin x is cos x, and yeah, you know these few things, assuming that. Let's continue this, right? So yeah, coming back to my main point, what if the variable on which a given function depends in itself is a function, right? Something like this. Say you have a function f of x which looks like log of x squared. Log x derivation you already know, right, which is 1 by x. Well, what do I do with log of x squared now all of a sudden, right? In such cases, chain rule comes in handy, and yeah, let's see how do we use it, right? And what better way to, you know, by just solving it, right? So let's try to find out the derivative of this with respect to x, of course. So when I write f dash of x, I'm trying to differentiate and or finding the derivative of this function with respect to x is what I'm trying. Alright, so first of all, in such cases, if log of x is 1 by x, derivative of log of x is 1 by x, what if I had log of t with respect to time? Then it would be 1 by t, right? If you had this, say, log of t, its derivative with respect to time, d by dt of log of t, if you had that, then it will simply be 1 by t, and so on, right? Whatever variable is, just 1 by that would be the derivative of log function. So you have this function. So derivative of log of x squared would definitely be 1 by x squared. 1 by x squared. Except this is not just x. This in itself, x squared in itself, is yet another appreciable function. It's an important function, y equal to x squared. This in itself is capable of being a potential function in itself. That right there, the x squared itself could be another function. So what you do in such cases is, first you differentiate the outer function, like the real function, which is, or I'd like to call it the boss function. The log function is the real function here, right? But within that you have a function of x squared. Then you first differentiate that, and then once again differentiate the inner function, the x squared, and you know the differentiation of x squared is 2x, and that will be your answer, right? So you can just simplify it further. However, wait, I would like to add a little something which we usually don't, but I like to mention that. Now focus here, one more thing. So looks like the outermost function was, or the boss function was, log. All right, you read that, 1 by x squared, good job. Then looks like there is a hidden function in there, so which is like x squared in itself. You differentiated that, fine. And chain rule, basically what you do in chain rule is, you go on differentiate the boss function first, then differentiate the subordinate function, then if there is one more function, then differentiate that also. It will be clear in subsequent examples, right? So you have 1 by x squared into 2x into, wait a second, x squared in itself is a function, fine, but don't you think x squared, which depends on x, don't you think x in itself, you could actually, maybe y dash is equal to x, don't you think x in itself is yet another function? Yeah, clearly, you can plot y is equal to x as this graph right here. This right here is y is equal to x graph, right? So actually there are three functions, one within another. First one is log, second is the x squared part of it, and third is x in itself. So you have to differentiate x with respect to x, but luckily differentiation of x with respect to x is just dx by dx. You can just write it like that, right? Dx by dx, differentiation of x with respect to x is simply dx by dx. And remember, what I'm trying to tell you here in chain rule is that you just go on differentiating one function after the other and multiply them all, right? That's how the chain rule works. And luckily dx gets cancelled and you don't really have to worry about that, and therefore your f dash of x of log of x squared is 2 by x. That is, after simplifying this you'll get this. Okay, that's how chain rule works. Let's do one more problem. Here goes. Find the derivative of log of sine of x squared with respect to x. Alright, let's try that. Chain rule. You can in fact pause and try this. So let me try to find the f dash of x. Once you get the hang of it, chain rule is nothing, you're done in no time. Yeah, alright. Who's the boss function here? The log itself. Alright. Then what is the first subordinate of the log function? It is a sine function right there. And what's the final subordinate? X squared. Actually, the ultimate final subordinate is x in itself. But you don't really have to worry about x like you saw in the previous case. You know, x will always evaluate itself as dx by dx and becomes 1. So you don't really have to worry about the x itself. So we have 3 functions, and if you technically look at it, we have 4 functions within function. But here let's write. So first of all, derivative of log x is 1 by x. So derivative of log of sine x squared would be, to begin with, at least 1 by sine of x squared. This is not sine squared x, guys, this is sine x squared. Alright, so you have to keep it that way, sine x squared. Alright, so log is done, fine, finally. What about sine x squared now? You know that the derivative of sine x is cos x. So derivative of sine x squared would be cos x squared, into, are we done? No, we are far from done. We still have the third inner function, which is x squared in itself. Now what? Differentiate x squared with respect to x, which is 2x. And finally, you don't really have to do this final part, that is differentiating x in itself, right? If you differentiate x, it is just dx with respect to, don't forget that you are differentiating this with respect to dx itself, with respect to x itself. So it will just be that. And if you finally simplify it, it will look, f dash of x will look like cos x squared by sine x squared into 2x. So that right there will be your answer. So you can just mention that here. I hope you got the idea, right? One interesting place where I can actually use chain rule is this. Find the derivative of, so I'll not write the entire sentence. Find the derivative of, let me take a function that looks like this. It looks like sine ax, sine of ax, where a is a constant, where a is just a constant. Using chain rule, of course, you can use chain rule and evaluate this. And once you do that, you'll always remember the value of sine a, derivative of sine ax. You can just remember that. It's good to remember that actually. Let's do it. So sine ax, you want to find f dash of x for sine ax. First of all, the outermost function. What's the differentiation of sine ax? It is cos ax, right? So you have cosine ax, cosine ax. Are we done? Not really. You have an inner function which is ax. So just you have to find the derivative of that and multiply that, the derivative of the inner function with the actual derivative, right? So you have derivative of ax is actually just x. I'm sorry, is just a. So you will get a multiplied with the whole thing. So derivative of sine ax is a cos ax, and you can, and therefore derivative of cos ax would be, it's why I'm mentioning these things is because f dash of x would be minus a sine ax if your f of x was sine x, was cos x, cos ax, I'm sorry, it's cos ax. So derivative of cos ax would be minus a sin ax, and derivative of sin ax is a cos ax, and it's true for anything actually, right? Let me give you a realistic function, just the last one. This will be, let's say you have a function. I'll use y for a reason that we have this in physics. A function y is equal to a sin omega t plus phi. So you have this function, right? So find the derivative of this function with respect to time. Find the derivative of this function with respect to time. Actually, a little information about this right here is, this is an expression of simple harmonic motion, where y is displacement of the particle in y direction, a is the amplitude of oscillation, and since it is amplitude, this will be a constant. So a is going to be a constant. I'll just remember that a will be a constant. Omega is angular frequency. So unless somebody is touching the already oscillating object, applying force or something, omega, the angular frequency, is going to be constant. Time obviously is changing, time never stops. And phi is called initial phase. Don't worry about all these terms, the only thing you need to know in this is that a is constant, omega is constant, and phi is constant, at least in the case that I have given. A, omega and phi are constant. Yeah, with this, find the derivative of y with respect to time. So let's do this. So you will have f dash of x, it's a function of time, right? And we are differentiating this with respect to time only. So I'll actually write it as d by dt of y. So it's basically dy by dt is equal to, and actually this is a good habit of writing it like this. It really helps. D by dt of, now you'll actually substitute the value of substitute the real function there. So a sin omega t plus phi, d by dt of this you are trying to find, d by dt of this function, right? Let's evaluate this. So I'll call it y dash. Y dash actually represents that I'm differentiating this with respect to time. Remember that we are differentiating this with respect to time always. Yeah, I'll tell you reason why a can be kept outside, but yeah, a can be kept outside. The derivative actually it's not actually keeping outside. We'll talk about that later. Yeah, so you have d by dt of sin omega t plus phi. Now it's like all you are finding the derivative of is sin omega t plus phi. What's the derivative of sin omega t plus phi? It's going to be cos omega t plus phi, just that, right? Cos omega t plus phi. But are we done? No, we are far from done. We still have the inner function which looks like omega t plus phi. So once you have got this, you will be in your mind doing this. I'll use a different color for that. In your mind, once you have done finding the derivative of sine, the boss function here in this case, once you are done finding the derivative of that, you will now be worried about finding the derivative of this inner function, this bracket right here, right? So in your mind you will be doing this, d by dt. Not really, you don't really have to do it in your mind. In the beginning you can actually do it with actually writing it. So you want to find that d by dt of omega t plus phi, and like I've already mentioned, omega and phi are constants. So if I want to find the derivative of this, derivative of omega t actually is just omega, because it's t to the power 1. So derivative of t to the power 1 is going to be, what is derivative of x to the n? N into x to the power n minus 1. So it's going to be 1 into t to the power 1 minus 1. So t to the power 1 minus 1 is t to the power 0, which is just 1. So 1 into omega is going to be just omega, plus derivative of phi. Phi, like I said, is constant, right? So derivative of constant is anyway constant. So you are only going to have omega, and that omega, don't forget to multiply it with this, right? So y dash in this case looks like a omega cos omega t plus phi. A little something here, actually, once again, to prove my point that derivatives actually are really helpful. This right here, like I said in the beginning, is equation for position of a particle in simple harmonic motion, basically oscillation. At this stage I can say oscillation. Alright, so particle which is oscillating, this is the position, this is a position. Okay, but you already know this, that when you differentiate position with respect to time, when you differentiate position, doesn't really matter position is along x or y, when you differentiate position with respect to time, what do you think you'll get? You'll get velocity. You get velocity, right? So, and actually that's what you have done. Y dash is nothing but dy by dt. So in fact what you unknowingly just did is that you got an expression for velocity, got the expression for velocity of SHM, or simple harmonic motion, which turns out to be a omega cos omega t plus phi. See, I told you it's useful, the derivatives, right? So you knew the positions expression and you got the expression for velocity, and that's chain rule right there. Keep practicing more examples for chain rule. I'll just give a few for you to practice. Maybe you can write the answers. I'll try to get back to you, right? So some chain rule questions are, I don't know off the top of my mind, let's say sine of, find the derivative of all these functions, sine of e to the x, second log of e to the x, tan of log x. And you will not be facing these rules actually, much of it. And use the chain rule, an interesting thing, use the chain rule for, once again just try the chain rule for this. Find the derivative of x to the power 4 with respect to x, and all these derivatives I'm telling you is to find with respect to x only. Find the derivative of x to the 4 once, except this time try to use chain rule and see if you'll get same answer or not, right? Whatever, fine. So yeah, that's that. Thank you.